Are you living in a computer simulation? Nick Bostrom, 2001, May, Abstract. This paper argues that at least one of the following propositions is true. 1. The human species is very likely to go extinct before reaching a post-human stage. 2. Any post-human civilization is extremely unlikely to run a significant number of simulations of their evolutionary history or variations thereof. 3. We are almost certainly living in a computer simulation. It follows that the transhumanist dogma that there is a significant chance that we will one day become posthumans who run ancestor simulations is false, unless we are currently living in a simulation. A number of other consequences of this result are also discussed. Preliminaries. Substrate independence is a common assumption in the philosophy of mind. The idea is that mental states can supervene on any of a broad class of physical substrates, provided a system implements the right sort of computational structures and processes. It can be associated with conscious experiences. It is not an essential property of consciousness that it is implemented on carbon-based biological neural networks inside a cranium. Silicon-based processors inside a computer could, in principle, do the trick as well. Arguments for this thesis have been given in the literature, and although it is not entirely uncontroversial, we shall take it as a given here. The argument we shall present does not, however, depend on any strong version of functionalism or computationalism. For example, we need not assume that the thesis of substrate independence is necessarily true either analytically or metaphysically, just that in fact, a computer running a suitable program would be conscious. Moreover, we need not assume that in order to create a mind on a computer, it would be sufficient to program it in such a way that it behaves like a human in all situations, including passing Turing tests, etc. We only need the weaker assumption that it would suffice for generation of subjective experiences if the computational processes of a human brain were structurally replicated in suitably fine-grained detail, such as on the level of individual neurons. This highly attenuated version of substrate independence is widely accepted. At the current stage of technology, we have neither sufficiently powerful hardware nor the requisite software to create conscious minds in computers, but persuasive arguments have been given to the effect that if technological progress continues unabated, then these shortcomings will eventually be overcome. Several authors argue that this stage may be only a few decades away. Drexler 1985, Bostrom 1998, Kurzweil 1999, Moravec 1999. Yet for present purposes we need not make any assumptions about the timescale. The argument we shall present works equally well for those who think that it will take hundreds of thousands of years to reach a post-human stage of civilization, where humankind has acquired most of the technological capabilities that one can currently show to be consistent with physical laws and with material and energy constraints. Such a mature stage of technological development will make it possible to convert planets and other astronomical resources into enormously powerful computers. It is currently hard to be confident in any upper bound on the computing power that may be available to post-human civilizations. Since we are still lacking a theory of everything, we cannot rule out the possibility that novel physical phenomena not allowed for in current physical theories may be utilized to transcend those theoretical constraints that in our current understanding limit the information processing density that can be attained in a given lump of matter. But we can with much greater confidence establish lower bounds on post-human computation by assuming only mechanisms that are already understood. For example, Eric Drexler has outlined a design for a system the size of a sugar cube, excluding cooling and power supply, that would perform 1021 instructions per second. Drexler 1992. Another author gives a rough performance estimate of 1042 operations per second for a computer with a mass on order of large planet. The amount of computing power needed to emulate a human mind can likewise be roughly estimated. One estimate, based on how computationally expensive it is to replicate the functionality of a piece of nervous tissue that we already understand, contrast enhancement in the retina, yields a figure of center 14 operations per second for the entire human brain, Moravec 1989. An alternative estimate, based the number of synapses in the brain and their firing frequency, gives a figure of 110, 116, 1017 operations per second, Bostrom 1998. Conceivably, even more could be required if we want to simulate in detail the internal workings of synapses and dendritic trees. However, it is likely that the human central nervous system has a high degree of redundancy on the Merkel scale to compensate for the unreliability and noisiness of its components. One would therefore expect a substantial increase in efficiency when using more reliable and versatile non-biological processes. If the environment is included in the simulation, this will require additional computing power. How much depends on the scope and granularity of the simulation. Simulating the entire universe down to the quantum level is obviously infeasible, unless radically new physics is discovered. But in order to get a realistic simulation of human experience, much less is needed. Only whatever is required to ensure that the simulated humans, interacting in normal human ways with their simulated environment, don't notice any irregularities. The microscopic structure of the inside of the Earth can be safely omitted. Distant astronomical objects can have highly compressed representations indeed. Verisimilitude need extend to the narrow band of properties that we can observe from our planet or solar system spacecraft. On the surface of Earth, macroscopic objects in inhabited areas may need to be continuously simulated. Microscopic phenomena could likely be filled in on an ad hoc basis. What you see when you look in an electron microscope needs to look unsuspicious, but you usually have no way of confirming its coherence with unobserved parts of the microscopic world. Exceptions arise when we set up systems that are designed to harness unobserved microscopic phenomena, operating according to known principles, to get results that we are able to independently verify. The paradigmatic instance is computers. The simulation may therefore need to include a continuous representation of computers down to the level of individual logic elements. But this is no big problem, since our current computing power is negligible by post-human standards. In general, the post-human simulator would have enough computing power to keep track of the detailed belief states in all human brains at all times. Thus, when it saw that a human was about to make an observation of the microscopic world, it could fill in sufficient detail in the simulation in the appropriate domain on an as-needed basis. Should any error occur, the director could easily edit the states of any brains that have become aware of an anomaly before it spoils the simulation. Alternatively, the director can skip back a few seconds and rerun the simulation in a way that avoids the problem. It thus seems plausible that the main computational cost consists in simulating organic brains down to the neuronal or subneuronal level, although as we build more and faster computers, the cost of simulating our machines might eventually come to dominate the cost of simulating nervous systems. While it is not possible to get a very exact estimate of the cost of a realistic simulation of human history, we can use num 1032, 1035 operations as a rough estimate for. As we gain more experience with virtual reality, we will get a better grasp of the computational requirements for making such worlds appear realistic to their visitors. But in any case, even if our estimate is off by several orders of magnitude, this does not matter much for the argument we are pursuing here. We noted that a rough approximation of the computational power of a single planetary mass computer is 1042 operations per second, and that assumes only already known nanotechnological designs, which are probably far from optimal. Such a computer could simulate the entire mental history of humankind, call this an ancestor simulation, in less than 10^7 seconds. A post-human civilization may eventually build an astronomical number of such computers. We can conclude that the computing power available to a post-human civilization is sufficient to run a huge number of ancestor simulations, even it allocates only a minute fraction of its resources to that purpose. We can draw this conclusion even while leaving a substantial margin of error in all our guesstimates. Post-human civilizations would have enough computing power to run hugely many ancestor simulations, even while using only a tiny fraction of their resources for that purpose. Moving on to the second chapter, the simulation argument. The core of the argument that this paper presents can be expressed roughly as follows. If there were a substantial chance that our civilization will ever get to the post-human stage and run many ancestor simulations, then how come you are not living in such a simulation? We shall develop this idea into a rigorous argument. Let us introduce the following notation. The expected fraction of all observers with human-type experiences that live in simulations is then. Since the experiences that an observer has, if she is living in a simulation, are indistinguishable from those she has if she is living in unmediated physical reality, it follows from a very weak form of the principle of indifference that the probability of her living is a simulation equals the fraction of observers that live in simulations. Thus, writing for the fraction of post-human civilizations that are interested in running ancestor simulations, or that contain at least some individuals who are interested in that and have sufficient resources to run a significant number of such simulations, and for the average number of ancestor simulations run by such interested civilizations, we have, and thus, because of the immense computing power of post-human civilizations, Ni is extremely large, as we saw in the previous section. By inspecting, we can then see that at least one of the following three propositions must be true. Well, that's all for today. I hope you enjoyed my short story about Nick Bostrom's article. By the way, in the description under the video, I left a link to its official website and the original PDF file for your review. On this channel, I will publish various scientific presentations and views that I personally support. Well, if you do not agree with this hypothesis, leave your comment under the video. I will definitely read everything. See you soon, brother.